Right now, somewhere out in the cosmos, there exists an object so impossibly massive and moving so incomprehensibly fast that it defies everything we thought we understood about how the universe works. This is not some hypothetical scenario that physicists scribbled on a chalkboard decades ago. This is real, it has been confirmed, and it is currently tearing through the cold, empty expanse of intergalactic space at 2.2 million miles per hour. It is a black hole, but not just any black hole. This is a supermassive black hole, a gravitational monster that weighs as much as 10 million of our suns combined. And it has been cast out from its home galaxy, sentenced to wander the void forever, leaving behind it the most extraordinary calling card imaginable. Behind this runaway black hole stretches a glowing trail of light that extends for 200,000 light years across the darkness. That ribbon is twice the width of our entire Milky Way galaxy. And what makes this trail so remarkable, what makes this discovery so profoundly strange, is what that light represents. It is not just energy. It is not just radiation bleeding out into space. That trail is composed of newborn stars, hundreds of them, thousands perhaps. These stars are being actively born, sparked into existence in the wake of something that was never supposed to create anything. Black holes destroy things. They consume them. They swallow light itself. They crush stars under their immense gravity and pull everything down into oblivion. So why, scientists ask themselves, is this particular black hole leaving a ribbon of creation behind it, woven from stellar nurseries that should not exist? When astronomers first glimpsed this phenomenon in their telescope data, they thought their instruments had malfunctioned. They thought there was an error in the calibration, a glitch in the system, something, anything that could explain away what they were seeing because what they were looking at should not be possible. According to everything we understand about physics, according to our best mathematical models and our deepest equations, a black hole is supposed to destroy matter. It is supposed to swallow light and crush stars and consume everything around it. That is what black holes do. That is their fundamental nature. So the discovery of a black hole that was doing the exact opposite, that was generating stars instead of annihilating them, that was moving through empty space at velocities that seemed impossible for something so massive, challenged the very foundations of what we thought we knew. But the mystery went even deeper than that. There was another question, perhaps even more fundamental. What force in this universe, what power, what mechanism could possibly be strong enough to take something as massive as a supermassive black hole, something that weighs 10 million times more than our sun, and throw it completely out of its home galaxy? What catastrophic event could have the strength to expel such an object into the intergalactic void? The answer to that question was just confirmed. And it changes more than just what we know about black holes. It changes what we know about the universe itself and the violent, dynamic processes that shape it. This extraordinary story begins the way the best scientific discoveries often do, completely by accident. In the year 2023, a team of astronomers working at Yale University and led by a researcher named Peter Van Dam were conducting what they thought would be routine work. They were sifting through old archival images captured by the Hubble Space Telescope years before. They were not looking for black holes. They were not searching for exotic phenomena or revolutionary discoveries. They were doing the kind of everyday work that astronomers do all the time when they are mining archival data. They were hunting for star clusters in a dwarf galaxy that was completely unrelated to what they would eventually find. It was ordinary work, the kind of thing that would have been forgotten as soon as it was finished. Then someone noticed something in one of the images that had absolutely no reason to be there. It was a streak, a perfectly straight line of light, as if someone had taken a ruler and drawn a thin, glowing line across the black canvas of deep space. The first thought that crossed the minds of these experienced astronomers was that they were looking at a cosmic ray, which is simply a charged particle that had slammed into the telescope's camera sensor. This happens constantly in space. It happens all the time. When this occurs, it usually leaves a white scratch across the digital image that looks immediately suspicious to anyone who has spent time analyzing telescope data. It is so common, in fact, that telescopes routinely take multiple exposures of the exact same patch of sky specifically for this reason. They take multiple images so they can identify these false signals and discard them. You simply check the other exposures. If the streak is gone in the next image, then you know it was just a cosmic ray, and you move on to whatever else you were looking for. Except this streak did not disappear. The astronomers checked the other exposures of the exact same patch of sky, taken at different times, and the streak was still there. It was still present in precisely the same location. It was pointing like an arrow at a distant galaxy system that was roughly 8.8 billion light years away from us. It was real. And that was when the problem began, because straight lines at this scale, at the scale of hundreds of thousands of light years, simply do not exist in nature. Galaxies are not straight. They are spirals. They are disks. They have structure and complexity. Gas clouds scatter in all directions, even the plasma jets. that are fired out from active black holes, even those tend to curve and spread as they travel through space. They do not maintain a perfectly straight trajectory. Nothing in the universe, according to everything we know, draws a clean, perfectly straight line extending for 200,000 light years across the void. Nothing, that is, except for something that is moving in a single direction at an enormous speed, traveling at such velocity for such an extended time, that it leaves a perfectly linear path behind it. With cosmic rays eliminated as a possible explanation, the team of astronomers began working through the other alternatives. They considered whether this could be a plasma jet fired out from an active black hole. That was theoretically possible, but jets at this particular distance do not usually produce the kind of signature that they were observing in this image. They considered whether this could be a flat galaxy that was positioned perfectly edge-on from our perspective, where the disk of the galaxy lines up precise, lie with our line of sight, and creates that thin streak of starlight. That was also technically possible, but the shape was all wrong. The streak was too thin and too uniform. The light profile did not match what you would expect from a galaxy. One by one, the mundane explanations fell away. The reasonable alternatives were eliminated, and the strange explanation kept surviving. The hypothesis that kept fitting the data was the one that nobody had ever directly observed before. It was the idea that a supermassive black hole had somehow been ejected from its home galaxy, torn away from the gravitational anchor that should have kept it in place. This object was tearing through intergalactic space, dragging a trail of gas and newborn stars behind it as it went. This had been a theoretical prediction for over 50 years. Since the 1970s, theoretical physicists had been calculating on paper whether it was possible to eject a supermassive black hole from a galaxy under certain extreme conditions. They had worked out the mathematics. They had determined that yes, under the right circumstances, it could happen. But in half a century, in all the years that followed that initial prediction, nobody had ever found direct evidence that this actually happened in the real universe. It was the kind of prediction that sits in textbooks and gets described as theoretically possible, and then mostly forgotten because the universe has rarely been generous about producing clean evidence for the stranger things that it supposedly does. Now, something that looked exactly like a runaway supermassive black hole was sitting in Hubble data, pointing at a galaxy 8.8 billion light years away. The evidence was literally on their computer screens. Hubble had shown them that this streak existed. It was undeniably there. But what they needed next was a telescope powerful enough to measure what was actually happening at the very front of that streak, at its leading edge. They needed to know what was happening where this object was actually moving through the gas and the matter of intergalactic space. Because if this really was a black hole moving at supersonic speeds through gas, there should be a very specific and detectable signature at its leading edge. There should be a shock wave, the same kind of pressure buildup that you get in front of anything that moves faster than the speed of sound in a medium. To see the signature, to measure it, to confirm it, they needed the James Webb Space Telescope. They needed the most powerful observatory ever pointed at the heavens. When JWST pointed its instrument at the tip of this mysterious streak, everything changed. The instrument they used, called the NIPEC, is extraordinary in what it can do. It does not simply photograph what it sees the way a conventional camera would. Instead, it breaks the light apart into its component wavelengths. It is like taking a beam of light and running it through a prism, separating it into all its constituent colors and frequencies. But the NIPEC does far more than that. It reads the chemistry and the motion of whatever produced that light all at the same time. It can tell you what elements are present, how fast they are moving, what temperature they are at, and 1,000 other details about the physics happening at the very tip of this cosmic phenomenon. When the data came back from a telescope orbiting the Sun about 1 million miles from Earth, the results were dramatic and undeniable. Right at the very front of the streak, the gas showed an enormous sudden velocity jump. There was a speed change of 600 kilometers per second, packed into an extraordinarily small region of space. That kind of sharp, localized velocity spike, that sudden change in motion over such a small distance, has exactly one explanation in physics. Something massive is moving through that gas at supersonic speed. Something is slamming into the gas and compressing it like a wall. The black hole itself is acting like a battering ram, pushing through the intergalactic medium so fast that the gas cannot get out of the way. It piles up, it gets compressed, it gets heated to extraordinary temperatures. When scientists analyzed the shape of the shock wave, when they looked at the temperature of the gas, when they examined the geometry of the entire structure, everything pointed in exactly the same direction. Every measurement confirmed the same story. The JWST had just confirmed the first runaway supermassive black hole ever found with direct observational evidence. Scientists gave it the official name RBH1, which stands for Runaway Black Hole 1, a designation that carries an implicit acknowledgement, with the expectation now is that this will not be the last. This discovery, confirmed in late 2025, with findings published in the astrophysical journal Letters, represents the first direct confirmation of a runaway supermassive black hole identified through its supersonic bow shock. Let us sit with the scale of what this means for a moment. The shock wave at the front shows a velocity jump of 600 kilometers per second. That is just the compressed gas being driven ahead of the moving object. The black hole itself is moving at approximately 1,000 kilometers per second. That is roughly 2.2 million miles per hour. It is 3,000 times the speed of sound at sea level here on Earth. At that velocity, this object could travel from the Earth to the Moon in about 14 minutes. It could cross the entire width of our solar system in just a few days, and it has been maintaining this speed for around 70 million years. Based on how long the star trail behind it suggests it has been in motion since it was ejected from its galaxy. The truly mind-stopping part of this story is that this thing is not just flying through space at this incomprehensible velocity. It is actually building something behind it. The trail stretches out in a 200,000 light-year glowing path through the darkness. This is not just a wake of energy. This trail is filled with newborn stars. Hundreds of them are actively forming right now at this very moment, sparked into existence by the wake of a supermassive black hole that was theoretically supposed to destroy things, not create them. Understanding why this is happening requires understanding the environment that this black hole is tearing through. It requires us to reconsider what we thought we knew about the space between galaxies. Most people, when they think about intergalactic space, picture pure vacuum. They imagine absolute nothingness. They think of the regions between galaxies as empty, devoid of all matter and energy. And compared to the densely packed interior of a galaxy, intergalactic space is indeed incredibly thin and sparse. It is far less dense than anything we encounter here on Earth. But it is not empty. It is not a pure vacuum. There is an extremely diffuse gas that fills the regions around and between galaxies. Scientists call this the circumgalactic medium. It is barely there. It is spread so thin that under normal circumstances, you would never notice it at all. An object drifting through this medium at ordinary speeds would barely interact with it. The gas would part calmly around it, like water flowing slowly around a rock in a stream. But RBH1 is not drifting. It is not moving slowly. It is moving faster than the speed of sound in that gas. And when you outrun the speed of sound in any medium, something dramatic happens. The medium cannot get out of the way fast enough. In front of the moving object, the gas piles up. It gets compressed. It heats up to extraordinary temperatures. It forms what is called a bow shock, a wall of superheated, compressed material. You see the same structure forming as a wedge-shaped wave in front of a supersonic aircraft cutting through the air. You see the same thing as a white wall of water at the front of a speedboat going fast enough to outrun the water's ability to flow around it. RBH1 is generating this bow shock at a scale that is almost impossible to visualize. Imagine a wall of compressed, superheated gas being pushed ahead of a 10 million solar mass black hole moving at 1,000 kilometers per second through the void. Then, behind the black hole, something equally extraordinary happens. The pressure drops. The gas that was being pushed and compressed and heated suddenly finds itself in the wake, in the area behind the moving object. The pressure falls away. The gas begins to cool. As it cools, it starts to clump together under its own gravity. When those clumps get dense enough, after tens of millions of years have passed, something remarkable occurs. The pressure at the center of each clump gets high enough to trigger nuclear fusion. Stars are born. One after another, they form in sequence, strung up behind the black hole in a 200,000 light-year thread of stellar nurseries. These are stars that have no galaxy to call home. They are stars that will spend their entire existence as rogues, drifting through intergalactic space, having been born out of nothing but the wake of an ejected monster. This is what JWST saw at the tip of that Hubble streak. This is exactly what is happening. Researchers confirmed in late 2025 that this is the reality of what we are observing. The lead author, Peter Van Dokkum, and his team provided what they described as the first direct confirmation of a runaway supermassive black hole identified via its supersonic bow shock. Now, the question that scientists have been wrestling with since December 2025, when this confirmation was announced to the world, is not whether RBH1 is real. That is settled. That is no longer debatable. The question is how something like this actually happens. What force in this universe is strong enough to kick an object weighing 10 million times the mass of our sun out of an entire galaxy? The answer is gravity itself, but gravity operating in a situation of extreme violence that only occurs during galaxy mergers. Galaxies have been crashing into each other since the early universe. It is not unusual. It is not an edge case or an exotic scenario. It is actually one of the primary ways that galaxies grow and become larger. Our own Milky Way has gobbled up dozens of smaller galaxies over its lifetime. And in about 4 billion years from now, it is going to collide with the Andromeda Galaxy in a massive merger event. When galaxies merge, they bring their central supermassive black holes with them. And those black holes, pulled by each other's gravity, eventually spiral inward toward the center of the newly combined galaxy and begin orbiting each other in a slow dance that can last millions of years. There are two distinct mechanisms by which this situation can produce a runaway black hole. The first involves three black holes coming together. If a third galaxy joins the merger, bringing a third supermassive black hole into the mix, the three-body gravitational interaction becomes unstable. Three massive objects cannot maintain a stable orbit together. The mathematics of gravity do not permit it. There is no mathematical solution that allows three objects of similar masses to remain in stable, predictable orbits around each other. What happens instead is that two of the three form a tight pair, and the third gets flung outward with the energy transferred from that pairing. It is a gravitational slingshot at the scale of entire galaxies. The lightest of the three is almost always the one ejected, and it can be thrown out with enough speed to escape the gravitational pull of the entire merged galaxy system entirely. But the second mechanism does not require a third black hole. It is stranger and more violent. When two supermassive black holes finally merge, they release an enormous burst of energy in the form of gravitational waves, ripples in the fabric of space-time itself. These are the same waves that observatories like LIGO and Virgo detect here on Earth when stellar mass black holes merge. But when supermassive black holes merge, the energy involved is incomparably greater. The gravitational waves they produce are of staggering magnitude. If the two black holes have different masses and different spin orientations, the gravitational waves they release are not symmetric. More energy gets released in one direction than in others. This creates an asymmetry in the emission, and in physics, if you fire energy in one direction, you get a kick in the opposite direction. This is Newton's third law, but applied to the warping of space-time itself. If the asymmetry is large enough, this recoil kick can reach velocities over 1,000 kilometers per second, enough to send the newly merged black hole flying out of its galaxy and into the intergalactic void forever, never to return, never to be recaptured by the galaxy from which it came. Scientists published a study in Physical Review Letters in July 2026 that worked this problem backward from RBH1's known speed and trajectory. Using numerical relativity simulations and Einstein's general relativity equations, a team led by Tassif Islam at UC Santa Barbara reconstructed what the progenitor black hole merger must have looked like. Their conclusion was remarkable in its precision. The two original black holes that merged to produce RBH1 had a mass ratio of no more than about 6 to 1. The larger of the two was spinning rapidly with a dimensionless spin magnitude of around 0.75. The binary system was precessing, meaning it was wobbling on its axis as it spiraled inward before the two black holes finally merged approximately 70 million years ago. That specific combination of masses and spins, that particular configuration and motion, produced a gravitational wave recoil powerful enough to launch the remnant at almost 1,000 kilometers per second. Think about what that means. Scientists looked at a glowing streak of newborn stars in a Hubble image. They confirmed it with JWST. They measured its speed and geometry precisely. And then they ran the physics backward through Einstein's equations to reconstruct the properties of two black holes that merged 70 million years ago in a galaxy 8.8 billion light years away. They can tell you how fast those black holes were spinning. They can read the ancient history of a cosmic collision from the wake it left behind. Tassif Islam described it as rewinding the clock on a remarkable cosmic event. And the implications do not stop there. Researchers pointed out that mergers like the one that produced RBH1 would be exactly the kind of events that the future LISA mission, the Laser Interferometer Space Antenna, would detect. LISA is a gravitational wave detector that the European Space Agency plans to put into space. It is designed to detect gravitational waves from supermassive black hole mergers across the entire observable universe. The team calculated that a merger like the one behind RBH1 would produce a gravitational wave signal with a signal-to-noise ratio in LISA of over 1,000. These events are not whispers. They are shouts. They are massive detectable phenomena that will be discovered when we build the instruments capable of hearing them. But here is the part of this story that carries the most weight and the most profound implications. RBH1 was only visible because it happened to be flying through a patch of the circumgalactic medium dense enough to light up. The bow shock at the front, the star-forming trail behind, all of it depends on the black hole having something to slam into, something that creates visible light and measurable gas signatures that telescopes like JWST can read and analyze. Van Dam and his team were explicit about this in their published paper. If this same black hole were moving through a region of sparser intergalactic gas, there would be no shock, no trail, no streak in the Hubble data, nothing visible at all, and we would have no idea it was there. It would be completely invisible. Not just hard to detect. Actually invisible to every telescope we currently have. And here's what that means. Galaxies have been merging for over 13 billion years. The conditions that produce runaway supermassive black holes, two black holes merging with asymmetric spins, or three black holes interacting gravitationally, these are not rare exotic edge cases. They are natural byproducts of the way galaxies form and grow across cosmic time. If ejections like RBH1 are a predictable outcome of galaxy mergers, and the physics strongly suggests that they are, then this cannot be the only one. There should be others, many others, black holes weighing 10 million solar masses, 100 million solar masses, perhaps even a billion solar masses, launched from their galaxies at extreme speed, crossing intergalactic space right now with no star trail to betray their presence, dark and silent and completely invisible. The universe may be full of them, and we would have no way of knowing. We would have no way of detecting them unless they happened to pass through a region of visible gas. The researchers who confirmed RBH1 specifically flagged this as the next urgent problem that needs to be solved. Van Dam and his colleagues noted in their paper that the most powerful instruments for finding more cases are the Wide Field Survey telescopes currently operating or about to operate. The European Space Agency's Euclid telescope has already catalogued over 1.2 million galaxies in its first year of operation alone. It is scanning the sky in a systematic way that could reveal the glowing trails of more runaway black holes if they happen to be flying through visible gas. And NASA's Nancy Grace Roman Space Telescope, which completed construction in late 2025 and is preparing for launch, has a field of view 100 times larger than JWST. It has the sensitivity to search enormous swaths of sky for exactly these kinds of linear features. Roman was specifically cited by Van Dam as one of the obvious instruments that could turn this from a single confirmed discovery into a population study, allowing us to finally answer the question that science has been asking since RBH1 was confirmed. How often does this happen? We would dearly like to know, Van Dam said. That question matters for a reason that goes beyond mere curiosity. Right now, we have confirmed one runaway supermassive black hole, but this confirmation only happened because of a chain of coincidences. The object happened to be in old Hubble archival data. Someone happened to be scrolling through images of a completely unrelated target and happened to notice a strange streak. The streak happened to be located in a region of gas dense enough to produce a visible trail. JWST happened to be operational and available to follow up. If any one of those conditions had been different, RBH1 would still be a theoretical prediction on a chalkboard. It would still be just something that physicists said was possible, but that nobody had ever actually observed. How many are we missing? If even a small fraction of galaxy mergers over 13 billion years produced ejected supermassive black holes, the number could be staggering. And most of them are sailing through the emptier regions of intergalactic space right now, completely undetectable, living in darkness, invisible to our best instruments. We built our entire model of how galaxies work around the assumption that supermassive black holes stay at the center. We assumed they anchor the galaxy. We believed that the relationship between a galaxy and its central black hole is permanent and fundamental, that it is unchanging and absolute. The confirmation of RBH1 does not destroy that model. The vast majority of supermassive black holes almost certainly do stay put. They remain at the centers of their galaxies throughout their existence. But it adds a new category. It adds a new kind of object to our catalog of the universe. A category of objects that got evicted. Objects that are out there somewhere, homeless and invisible, having left their host galaxies behind tens or hundreds of millions of years ago. The universe just got stranger and bigger and more violent. The thing that science predicted on paper over 50 years ago, and that no one had ever directly confirmed, was finally found, not by someone looking for it, by someone scrolling through archived telescope data, looking for something completely different, spotted because of a straight line that had no right to exist, confirmed because the most powerful space telescope ever built was pointed at its tip and read a shockwave in the gas. And now, with the physics reversed and reconstructed, we know the exact spin and mass configuration of two black holes that merged 70 million years ago in a galaxy 8.8 billion light years from here. Faster than almost anything else in the known universe, into the void, possibly forever. And somewhere out there right now, there are almost certainly more of them. Dark, invisible, moving, and we are only just beginning to build the instruments capable of finding them. We are only now reaching the technological capability to detect these extraordinary objects and understand how common they really are in our universe. This story that we have just told you, this discovery of a runaway black hole creating stars in its wake, this confirmation of something that theory said was possible but nobody had ever seen before, changes everything about how we view the cosmos. It reminds us that the universe is not the calm, steady thing depicted in textbook diagrams. It is not a quiet, orderly place with immutable laws and unchanging structures. The universe is violent. It is dynamic. It is filled with galaxy-scale collisions and black holes being flung across the cosmos. It is a place where stars are born in the wake of things that should only destroy. This is what the universe actually is.